have two sessions, and this session we talk about materialistic algorithms, and then the next session we will talk about how we can use them for a different level of machine learning algorithms. Okay, so as usual, I start uh, with the motivation, and the point is why we are going for just a minute, yeah, we are going for optimization, and our whole day is full of optimization. I don't know, yeah. So whether it's inventory management, or it's a lecture scheduling, or it's a home engineering problem like load management, or it's a machine learning algorithms, or you're working for aircraft, so aircraft crew scheduling, task scheduling in computers, or job scheduling in industry, travel salesman problem, and there are lot and lot of application. So our day start with some kind of a optimization process, and then throughout the day we do a lot of optimization things, but we do it from different perspectives. And if you see these things from a mathematics point of view, we do try to do or try to use one or another form of optimization. So when we talk about optimization, so the general goal of optimization is simple. That is basically we want to maximize or minimize certain thing. And that certain thing we call it an objective function. So we want to say maximize our profit. So I don't know. Just let me check it why the pointer is not coming. Second. Yeah, okay. There is an issue here. Yeah, yeah. Now it's okay. Okay, so we try to maximize our profits or minimize our energy consumption or minimize our losses. So we always keep on working between these kind of things that, okay, how to maximize certain thing and how to minimize certain thing. And the initial, we were introduced to kind of a calculus-based approaches if I talk about the high school level. And it is very simple that, okay, we'll say that, okay, what you can do, you find out the gradient, and that gives a stationary point, and then you uh, go for the second order derivatives, or something, so to confirm whether you are working on maxima or minima. Well, this is okay. This works fine, and from there we people call it a hill climbing approach. So so if you want to make it an iterative way of doing the things, so what you can do is you start at any point, find out the gradient, and then take a small step and keep on moving slowly till you reach at the point where there is the gradient becomes zero, and then you can say it's a maximum or minimum. Well, this works fine, this kind of arrangement, but you just check this figure. This figure gives us some kind of a challenge, because if I start from this left side of it and I keep on finding the gradient, at this point I'll see that the gradient becomes zero, and I'll say this is the maximum. Whereas if I start from this side, then okay, I'll keep on finding the solution and I'll say this is the maximum. So the problem is same, but now it is important from where we are starting. So if my choice of the starting point is good enough, then I can find out a good solution. But if my starting point is not good, it's bad, then I end up with the wrong solution. And you'll find that the things are very complex when we talk about the real world. You can see this picture or the bottom one. There are so many minimas and maximas. And if somebody asks you to find out where is the global minima, where is the best minima, it's difficult to find it out by this approach, which is basically we call it the calculus-based approach. So now we are talking about two different terms. One is local and global. And if you see this figure, again, you can see there are, if I see that Okay, if I start here and then I'm looking for a minima, I stuck it here. It's a very strong minima, but this is the minima only in a very restricted zone. We call it a local, strong local. And then, okay, somehow I move forward and then I find out another solution, which is the best in the whole region. We call it global. And here you can see this point to this point, all are at the same values. These are minima, but this is a weak local minima, and likewise. So we have different types of arrangements, different types of situations where we look for minima or maxima, but ultimate goal is to find out what is the how to reach to the global one. And if my scenario is like this, or if my scenarios are like this, then this approach, which is there on your screen, it's stuck up in a local minima, and we may not able to find out the global one. People try different ways. Let's talk about some few things there. So what we are looking for, we are looking for a global one, which is the best here, not the local one, and that is our target. Because if you see the benchmark problems, they are very typical problems. You see their graphs. You see the graphs there. Okay, if you if you try to find out a way, like iterative way of finding the minima, probably you cannot move here because the gradient is zero. Gradient is zero here, but there is a minima somewhere in between there. You can see there are very sharp edges here. You can see this picture, very sharp edge here, and another smooth functions here. So these figures, these are the benchmark problems. So if you are interested in developing a new algorithm on optimization, yeah, people ask you, okay, check it on these benchmark problems. So just check the figures there. That these figures are very interesting figure, and they have very spiky points. They have flat surfaces where your gradient and all these methods they stuck up. They're not able to perform well. So then people thought of like something different. Like, can we work on can we work with some search-based approaches? So search-based approaches, though what we have discussed, that is also a search-based approach, but they tried different combination of search-based. So initially is like a linear search. So this we have done that. Okay, I want to find out what is the minima point between the a single variable. So okay, what I do is I divide it into certain parts and find the values and likewise. Okay. Then there is another way of searching it. It's called brute force search. That okay, we at one point we find out, we take two values and then bifurcate it again and keep on searching the things to find out the solution. At the bottom, you can see it's written low. That the complexity is low here. Then there is a grid search. So okay, because this is the whole surface, you have to find out where is your solution. So you make a grid and start following it. That okay, I search it here and then move this much, then search, then move this much, search that, and likewise, you search whole of the surface. And I think you have observed grid search approach and application in machine learning models. If you have done some hands-on, they are applying a grid search methods also. Then a bit more complex, and that is basically breadth first search, and that is basically okay. We make we do the search in this way that okay, I'm here, and then there are 2 points. I search this way, and then divide it, and then go by the next layer, and it is like that. This is breadth first. Each search has a certain kind of advantage and disadvantage. Okay. And then there is a depth search, that my search mechanism is I go into the depth of it. So both methods have their own advantages. Let's check it. If I'm focusing here that this is G is the solution, so you can see that I search it like this and then I search it like this, I'll get the solution fast. But if I go for a depth one, so G is somewhere here, so I first search whole across these, then whole across these, and then it will take a time to reach to that point. So all these approaches, they have certain advantages and disadvantages, and that basically excite the researchers to find out every time a new way of solving the things there. Then people move for iterative deepening search. So the complexity is a bit more increases. Then uniform post search. Then best first search method, beam search, A star search, Monte Carlo search, taboo search. These are the different search techniques they have applied. Okay, so every search method has a certain kind of a policy, and it try to follow that policy or methodology to find out the solution. And you can see every time the complexity keep on increasing there. Continuing with this one, these are the certain search methods modified. People have applied in optimization. Now they try to do the search following certain pattern. So here you can see this one is basically crime scene search methods, they call it. So the pattern you can see here, it's very straightforward, go straight, likewise. This pattern is you go by the spiral way of searching the whole area. In this method, you go zigzag. In this method, you go by grid, like you start and then return, and likewise, and then such whole of this move back and such whole of the surface. This method is you divide your whole surface in zones and different zone, and then do the search in the zone. So it's a zone based search method. So all these methods, what they are doing is they are searching the things in this on a surface, because we believe that our solution is somewhere in the search surface. So surface is actually a bounded region which is constrained. So all the points in that search space, they are the solution of the problem. They are the solution of my optimization problem. But our goal is to find out the most optimal one. And that's why we do the search on in different zones, surfaces. And now this one is another way of representation. You start from here. Now this one is hill climbing. This is the gradient. This is the top view of the hill climbing. This is the peak. This is the bottom. So if you see the hill from the top, it look like that. So you start from certain point and then find out the gradient, move to the next, move to the next, move to the next, and reach there. This is also one form of a search, like this one. So how you move it, whether you are going like this or you are going this, there comes variants in that one. So the gradient and then accelerated gradient, and then Adam is also there. Lot of different methods are there, and these are basically if you check it in that way, these are the some form of search methods there. Okay, so some kind of a movement there, and that is how we do all these search methods. Okay, so these are just a representation of different search methods. So this one is a gradient descent I was talking about. You are here and then you find out the derivative, take a small step and move to the next point, follow this I think now you are quite aware of. X is X minus learning rate into gradient. This is weight updation, what we have done in neural network. You move to the next point and then again find out the gradient and find out the new point till you reach at the bottom. So this one is a gradient descent, but if you see it from different perspective, it look like the same, that it is also a search method, but from a different perspective. This view have studied. This is the beginning of our optimization. We were into most of us who are from India. We started our optimization from here. It's a linear constraint of problem. So graphical way of doing the things. Somewhere we started in class 8, and what we do is these are the constraint lines, and this is feasible region. And then what we do, we start from 0 0, and then move to the next corner point, find out the value, move to the next corner point, find out the value, move to the next point, find out the value, and then see which one is the giving us the maximum or this is also a search way, because here the policy is different. We start from 0 0, and where we are looking, we are not looking somewhere in between. We are looking at the corner, because these are linear programming problems. So we know that the maximum minimum exists at the corners. So we just check out the corner points there. Okay. And then we also subjected to this kind of a search where we talk about golden search of Fibonacci series methods and all that. And also we do it somewhere in our hit and trial method, try to find out the solution of higher degree polynomials. What we do is we assume something to, and then try to find out near around solution. So this is the same kind of setup that we have 2 points. We evaluate the value at the 2 points and then find out a middle point in between them, and then squeeze our zone of search and keep on searching these things. So if I talk about the golden search method, every time we half the search space. In Fibonacci series, we always we follow the Fibonacci method series to to reduce our search spaces. All these things are just to motivate that, like, okay, something is common there, because we are looking to develop or to see a new zone of optimization method, and that is heuristic or meta-heuristic algorithms. So this is a very important slide for everyone. And why it is there? Because this slide summarize what we have discussed so far. So in all the methods which we have discussed, there are three things. Okay, so if you want to develop new algorithm, focus on these three things. First, how we are starting our algorithm. So from where we are starting the search. That is the first thing. The second is the policy to move. In all the search methods, we have different policies. If I go back, you can see the policy here is different. Its policy is, okay, you go straight and then turn, and the straight, this policy is different. Here the policy is divided into zone. Here the policy is move from one point to another point depending upon the gradient, which is here. Here the policy is move from one corner point to the next corner point. Here so there is always a policy to move from one point to another point. That is the second thing. So like here, and the third one, let me finish those things. And the third one is how you stop your algorithm. So like in first here, I stop my algorithm once I reach to the endpoint. I stop my algorithm if I am able to explore all the zones. Here I stop my algorithm if the change in the gradient is 0. Here I stop my algorithm if I have tested all the corner points. And here I stop my algorithms if there is not much change in the solutions. So those are the three things which you will find common in all types of optimization algorithm. Okay, so first one is how to start. So like here in this one, we are starting randomly at random point. Okay, fine. The second one is how you change it, how you reach to the next point. So I have to find out delta x. So I have different ways of changing this. I have different ways to reach to the new point, which is old point plus delta x. So this delta x, I can use a gradient method, or I can go for momentum method or velocity method, or you can use neural network or something like that. So this is my policy to move. And the last point is how you are stopping your algorithm. Well, that is one thing, and please keep this thing in your mind when we will discuss the meta-heuristic algorithms. So heuristic is taken from the Greek word to find, and meta is basically the another level of solving the things. So meta-heuristic, we call it heuristic around heuristics. Why all these things comes into the picture? There are a lot of like explanations about why this method is better than the conventional method and all those things. The only thing here, we can put it like that. In conventional methods, when we put it, the challenges are there because of many things. Like if I'm talking about the gradient based methods, okay, let's start with a simple one. If I talk about graphical methods, which we have seen there, linear programming, but we know that simplex methods and all these, they are confined only for the linear problems, and we know that most of our problems are non-linear. So then we move to the non-linear, and then we know that what we use it for non-linear. Usually we use gradient approaches for non-linear, but there is a condition on that gradient must exist. So if the gradient is not existing, we have to find out a different way to solve. Either we make the problem continuous so that the gradient will be there, so then we approximate it, or we have to make the changes in the methodology to solve it, because for gradient based we need a problem to be continuous. But we know that in the real world, when we are using computers and all these devices and all these things, the problems are no more continuous. They are discrete. They are N-type, NP-hard type problems, which are difficult to solve that way. And that's why people move towards some materialistic algorithm. So some kind of, I have taken this kind of these things from some information from research articles and all that. So you can see here it's a TSP kind of a problem. So if you want to serve 15 customers and you want to find out the best visiting sequence, so you can see how many combinations are there. And then if I check about how many solutions my computer can find out per second, then you can see how many hours it will take. And if the problem is big, you can think of how much more time is required. So people talk about that there are limitations. Can we try with materialistic optimization? And that's why people try to develop these algorithms there. So materialistic, basically, there are various categories, and they are basically the logic is there is a certain kind of a inspiration from where the idea is taken. Okay, so we will talk about those inspiration, and you can see here if if few of algorithms they are inspired from nature, like genetic algorithm, ant colony optimization, honeybee algorithm, monkey, spider monkey, crow search. There are so many out there. So they are inspired from the things which are happening in the nature. They are known nature also, like taboo search and iterative local search methods. Then the another categorization you can put it is objective type, whether your objective is static or it's a dynamic. Third category, you can categorize them on the basis of the memory and memoryless. So few algorithms they keep the memory, few of the algorithms they are memoryless, they don't keep the memory. You can categorize these methods in form of the direction of the search, like single neighborhood. Most of them are single neighborhood, but you can talk about the multiple neighborhood also. And then how the evolution is done there. So you can talk about trajectory-based methods, or you can talk about the population-based methods. So here it is there, trajectory-based methods. So trajectory-based method is basically, you can see here, okay, the points are taken and the solutions are observed following certain level of a trajectory. So the categorization you can take is lot of algorithms are there, like local search, simulated annealing, taboo search, guided local search, and all these things. Population-based method, these are more popular. So in trajectory-based is more of mathematical part, the conventional mathematical part. Population methods are more of inspired from the nature category. So you will find population-based, I think in coming slide, I'll explain you in more detail. So these methods, you can see a lot of art examples are there, like, okay, evolutionary programming strategy, genetic algorithm, ant colony, honeybee, differential evolution, scattered search, particle swarm optimization, and all these things. What is the difference? So let's talk about the trajectory based. Okay, so the trajectory based, you can see this is the search space here. Okay, and all the points which are shown there on the in this box, they are the solutions. What our goal is to find out a most optimal solution. So now put it on that. We start with one. And so what are those three things? First thing is how to start. So randomly you take one point. So it's a random based start. And you'll find in most of the materialistic, the start is random based. Then later on, people try to merge the two. Uh, and and you will find that there's a reason for it, because this randomness help us in avoiding the local traps. But okay, let's start this algorithm. So the first thing is S0. So we have taken one point and randomly it is taken. Okay. And then what we will do is we create a circle around it. Create a circle around it means we will see what are, we decide one range, and in that range we will see that what are other points. So like here I have decided that, okay, what are near around 5 other values. Okay, and then I evaluate at those 5 values in that space. Okay, and then what I'll do is whatever is the best among them, all those 5, I'll take that value, my my that will be my new value. So the policy is very simple. To move from S0 to S1, what is the policy? The policy is you select near around values, and whatever is the best among them, you go to the next one. And when you reach to the next one, then you check near around values, and then find out which is the best and the best, and you keep on moving till the third point is addressed. And the third point is how to stop. And how to stop, there are various ways. One way is, okay, you say that, okay, I'll do this search, say 4,000 iteration, and then I'll stop. Whatever the solution, I stop there. That is one way of stopping it. The second one is, okay, there are not much change in my solutions or findings, so I'll stop. That can be another one. Or you can put a band around it, that, okay, if my solutions are repeated 5 times in this band, I'll stop it. So there are various ways. So this is trajectory based method. So you are here, then move here, and then move here, and then move. But there is a problem with this one, and the problem is, say the point here, which is this yellow point, which because of my settings, I'm not able to search it. So this point is left unsearched. Maybe this is the best solution. So that's the limitation of this approach. Then comes this, and we have seen it. This is a simple way of this thing. There is a trap, basically. What is the issue with this approach? So say I have this graph and I want to find out where is the optimal solution. So what I'll do is I'll take any random point to start with, and then I put a band over it that we call it a neighborhood, and then check at the corners of this neighborhood and find out which is the best value. So I'll take another point in this band and check it whether this value is better than the previous one. If it is better, I'll take this one as a optima, my new value. And then put another band and then check the new value. And then if this is better, I reach there. But now if I'm here, and if I take any value in this band, in this band, then I'm trapped here. And this is known as the local trap, whereas my good solution is somewhere here. That's why people go for different models and all these things. So this one is one kind of issue with this one. There are various ways to escape the local trap. Okay, so you can see local traps. These are the ways people have implemented. Few of them can be, you can start, instead of starting with one point, you can take a start with multiple number of points. That is one way of avoiding that trap. Or what you can do, if there is no change in the solution, what you can do is you push it, create a disturbance, push it so that it move to the another point, and from there it move to the another point, and likewise. So there are various strategies people have adopted. I just discussed only two of with you, but they have adopted it. But then there are issues. If I keep on doing like this, then I'm here, and if I want to disturb this point, I disturb it at a very large value, then it comes here. So how to stop it? Whether we will reach to a solution or not, or keep on searching like this. They put into the two category. One is, then they talk about diversification and intensification. So initially you start with the randomly diversified manner, and once you are reaching towards the solution, then you intensify your search. So you have made it dynamic. That's a good idea to converse your optimization algorithm. Okay, so moving further, so there are various ways This one is showing you perturbation approach, so that if you're trapped, this is trapped here, this is trapped here, you perturb it by certain kind of a function so that it come out of this trap and move to the next one. There are various properties when people have adopted there. The second approach is the population-based approach, and the population-based approach is simple. We choose certain population, okay, from here. So we take some population here, that okay, this is the first population, and then we do certain operation on this to generate new population, and then we evaluate it. We keep the best population with us, discard the poor, drop the bad population, and then we keep on doing this, repeating these things again and again. So here the start is random because we have started with the random population, and then the policy to move is, or policy to get a new point is, we create a new population by certain methodology, and then evaluate it and drop some bad population, and the stopping criteria is iterations, or what I have told you earlier also, that you fix it, that okay, I'll do it 1,000 times or 100 times, or and then I'll stop it. So today what I'm talking about is more on how you can design a meta heuristic algorithm, and then we will discuss uh, on some of the algorithms, these aspects, and let's talk about those things here. Okay. So, so here is a first algorithm, which is a genetic algorithm. Okay, so genetic algorithm, it was initially proposed in 1975 by Holland, and then it was popularized by Goldberg, who was the student who worked with Holland. So most of the people they know, like, okay, it's by Goldberg, but it is popularized by him. You can find a book on genetic algorithm by Goldberg, very nicely written book. So now let's talk about how it comes into the picture. So we need three things. One is how to start. So obviously here also we start randomly. So that is okay. The second thing is the policy to get a new point, or move from old solution to a new solution. And here they have used genetics, or the Darwin theory. So they have used a genetics here to move from one point to the another point. And the stopping criteria is again the same. And these three steps, if you complete it, then it's a genetic algorithm. So how it works? So this is the flow diagram. So let's understand how it works. So we have a set of solutions. Set of solutions means a solution in those range. Usually we represent the solutions in the form of this. This is a representation. So in nature, we as a human, we are made of chromosomes. In genetic algorithm, we represent it by strings. So these are the strings there. Okay. And then we are developed because of the reproduction. So here we call the reproduction as a crossover. Okay. And then there are mutations. So we call the same here mutation also. And then Darwin theory states that those who are fit, they will survive, rest will die out. So we take these three things from here, that there must be a reproduction to produce a new child. Fine. Then there are mutations. Mutations means something is happening somewhere, sudden change, some good or something bad. And then the third one is the survival for the fittest. These three things will help us to build a policy to get a new solution. Let's see how it will work. So out of these solutions, so solutions means, say you are solving a optimization problem, x1 plus 2 square plus x2 minus 5 whole square. Given x1 in the range of minus 5 to plus 5, x2 minus 3 to plus 3. So now we are constrained. What are the values of x1 and x2? in the range is given. So we take some value from there, some value from that band, that is a feasible solutions. So those are these one. And then we convert them into binary strings. Okay, so we have strings here. Now these are our solutions. So this is my initial population. These are the starting point. Then now we work for the policy to get a new point. So what is the first policy? Crossover. Crossover, how crossover occurs in humans? So we are made up of a kind of we study very simple way that genetics, we have XX and XY, and then XX and XY, when they combine with each other, they produce XX and XY combinations. And then XX and XY combination or genetic combinations, they are the properties of the children. So how to perform it here? So we do it like that. Okay, so this one is a say upper one is a say father and the lower one is the mother. Okay, and this point which is here in between point, we call it a crossover point. That means these genetic properties child to the child, these genetic properties will come from a father, and these genetic property come from mother, they produce a new child. And then the genetics property from father and the genetic property from mother, they produce another child. So a parent, two parents, they produce two types of child. Take it, it's a very simple way. So this crossover probability, this is again an agenda of research, that where you will do it. You will do it here or here and here. Well, that brings a certain kind of a discussions and then the variants and all those things in genetic algorithms. But let's understand its basic working there. So when they cross over it, so you can see the all gray part, and here and up and down, they produce one child, and non-gray they produce another child. There is something very interesting in it, and that is basically the child, they are carrying certain characteristics from the parent, and that is a good sign. In optimization, if we are searching a point, then some points, some characteristics of the old points, they are already captured in the new points. So this one is the new population here. But it's not completely done, because we have just completed the first operator, that is the crossover. Then we go for the mutation. Mutation means we create a certain change somewhere else. So like in this population, it is 0 and we make it 1. So it's swapping of the thing there. Okay. And then once these two operations are done, then these are the offsprings. So we have offsprings from the parents. And then we perform the survival for the fittest. So this is one way of doing it, which we call it the rotary wheel selection criteria. Okay, you can see a wheel is there. These are certain values, and if you rotate this wheel, we can easily say that the chances of getting this area, which is 40%, is more because the area is small. So in other way, we'll say this is more fit than this 5% one. So this kind of arrangement, we will do it here. Okay, once we complete this part, then what we will do is we will have new values here, and then these new values come here, and whatever the poor values, we remove those things, and then we keep on repeating this whole cycle again and again and again. Okay, and that is how we reach to the solution. This is genetic algorithm. So on the concept side, because today's I'm not explaining the genetic algorithm in depth, the concept side, you understand it that we take some values randomly, we created strings, then we perform an operation crossover, then we perform operation mutation, then we check the survival fittest, and then we repeat this cycle. Well, the interesting part here is with this algorithm, the interesting part here is you can do these these operations in any form. Like you can do crossover mutations and then selection. You can do selection, crossover mutation. You can do crossover, selection, mutation. In any combination, you can try it. But you have to complete these three things. So just to reach to the next cycle. This is how this algorithm works. There is another algorithm which is known as a differential evolution. Differential evolution was proposed in 96, and this one is a bit uh, modified version from the genetics. It is taken and it is modified in a way. Common things are almost same. You can see there is a mutation, there is a recombinations and the selections, all those things there. But the operation is a bit different. Okay, so as the name suggests, differential, that means we are taking a difference of few things and then we use it to evolve the new solution. So say these are the, you can see these are the, you can see these are column wise, these are certain values. So these are the target vectors, these are certain solutions. So I'll start with one, that okay, this is one of the solution. Now I want to modify it. So how I modify it? I'll take two other solutions randomly. So again, I'm doing all these things randomly. So I'll take two solutions randomly, find out the difference, that what is the difference between them, and then multiplied by f, that means by a gain. And after multiplication with the gain, I'll take another third one, also random one, and then I combine with this one. And after the combination, I will see whatever is there, whether which one is good. If earlier one is good, I keep it. If new is good, I'll keep it. So that is how I shift from 94 to a new value. Then I change my target vector. For next round, I'll go for this 23 with the first one as 44. And then I go for the next, then go for the next, and go for the next. And I keep on repeating these things. Since you can see here, the operation is basically we are taking a difference of 2. That's why the differential thing comes into picture. What is the advantage, and what is the advantage of doing all these things? The advantage is there. You see, if these points are, let me check here. So, okay, so this is my search space. I'm starting here, searching here. I take two random points here and here, and take another one here, and say if my solution is here, this side. Okay. So then if I find out the difference of these two, and then I'm taking these vectors with reference to certain point. So this is my one vector, and then these two are the other vectors. And if I'm taking a difference of these two, adding it to third one, okay, so then I find out that direction. Okay, so this one is one direction here, this one is another direction, and then this one is another direction. If I have found out the difference, then difference comes in this direction. So that will force the original one to move in this direction. And if I'm adding this one, then this vector help in moving in this direction. So it will reach to the solution a bit faster. That's the idea here. That's the idea, and this is the logic here, and this approach is known as a differential evolution approach. Then another very popular algorithm come into picture, which is known as particle swarm optimization, which is inspired from the swarms. Swarms means a group of species, they work together, and we also taken as a as a group of person. When we do perform certain activity, that is also swarm. So it's more of a behavior group, behavior science there. So just you imagine that how you search a particular thing in, if you are 5 friends and you lost something in a room, how you search it. So first thing, you randomly distribute. So that exactly what we do here also. And then you individually search, and then you tell each other that, okay, this I'm not able to get it, or I'm able to find it. Or if somebody tells you that, okay, this side there is a slope, there are more chances. That is exactly what we are doing here. So this is the point where you are searching. Okay, this is your, so you are searching and you are trying moving in this direction. Okay, so you're moving in this direction, but suddenly find that this side is much better. So you take a turn in that direction, and then some of your friends say that no, there are good chances to get it. Then you take a further turn in that direction, and you reach to a new point. So this is the policy to reach from old point to the new point. How you write it mathematically? Very simple here. This is your personal choice, and this is your current position. So you take a difference, that means you are trying to move in the direction of your personal choice. Plus, this is your whole group choice difference. This is your personal position. You are trying to go in that direction also, like this. So that comes from here. And this is your initial velocity. We multiply it random. Reason is there. Mathematically, the reason is to come out of the local traps. Philosophically and psychologically, every time we consider the preferences based upon our mood. It's not like always I consider 30% of this or 70% of this. Sometime I prefer 70% of my own choices, 30% of my social choices, sometimes something different. So that's basically we put it random. C1 and C2, they are the controlling parameters. You will find a lot and lot of PSO variants or new algorithms who worked on C1, how C1 and C2 to be controlled. Similarly, omega is also a controlling parameter. That will give me the change in the velocity, and if I multiply the velocity with time, that will give me position. Since this is iterative in a manner, so every iteration we complete it, so time t is 1 here. So we add this velocity to my old position, I'll get a new position. So you can see here that initially they are randomly distributed with different directions. And then with every iteration, their direction changes and they try to keep on moving. So after certain time, you'll see that here there are two groups. One group is here, this is another group, but you will see that here are, this is the best solution. So after some iteration, more iterations, you will find all the particles they reach to the solution. So this method is no more like earlier one, your genetics or D, that the best will remain there and the worst will die out. This one is more of a cooperative behavior. So they cooperate each other and then they help each other to move from one point to another. This happens in the birds, and then let people, two uh, engineering people, James Kennedy and Russell, electrical engineers, they proposed this algorithm in 1995. This is initially they put it in a conference, and then later on, this is one of the most popular algorithm in materialistic algorithms. And then people developed a variant. So if you are interested in developing a variant, you can do it there. With one way of doing it, you develop a certain kind of methodology, how to find the value of C2 or C1 or W, or how you can start with the algorithm. So variations, if you want to create it again, or variants you want to develop it, then you have to check the technique is start with where you want to create the change, whether you want to create a change in the initial choice start point, or you want to create a change in the policy to move from one point to another, or you want to create a change at the stopping criteria. So it totally depends on that, how you are creating those changes there. This one is another algorithm, which is again, which is inspired from ant colony. That is basically how ant works. Proposed in 1990 by Dorego. So the and we have also observed it. So you just sit down and see the how the ants are moving in a line, and then you put one obstacle like this, that one side it's small, another side it's tall. You'll find initially the ants they distribute both the sides, but after some time you will find them they are moving through the shortest one. So the interesting part here is the ants are blind, but still they are able to find out the shortest distance. People have performed very various experiments. So how they do it, and this how they do it, this technique lateral method people have used it to develop this optimization algorithm, which is known as ant colony optimization. So what happened is actually biologically, if you talk about when ant when move, they drop the forminon, and the forminon then help them because they keep on smelling it, and then based upon the forminon they move to the next point. Also, the forminon has a property that with time and with temperature it evaporates. Well, that is the only logic people have used it. So you can see these two ants are there, they drop some forminon, and then when they are going through it, so more ants will go, they will drop more forminon, and then this they divide themselves like here. So some forminon, but you will see that since this path is more, the evaporation will be more. So there is the intensity of forminon will be less. This path, the forminon will be more because the path is shortest. The intensity will remain, it's more than the second path, and that's why more ants will go through this one, and later on you'll find all are going through this one. This is the logic there, and this is how this algorithm is developed. So the policies initially again start is random. They randomly start the solution. Stopping criteria maybe the iterations you can put it. Let's take it. The policy in between is policy to move here is the concept of the phenomenon and its evaporation rate. So there you we have to develop this model this in mathematical form, that this process how this is happening, and that is being used here. Okay, so you can see here this is the mathematics, a simple mathematics which is being used to develop this one, and later people have developed many variants of this algorithms. This is another algorithm which is known as harmony search algorithm proposed by Gein, a relatively a new algorithm proposed in 2001. So this one is mainly on how the music is composed, and based upon that, this whole arrangement is done. So randomly we start, stop is there, but how the music is composed, that is the policy to move. So here you can see this one is Greek. So you can see there are three instruments: do, mi, sol. So for a mathematician or for an engineer or optimization person, these are the three different variables with certain values. And so we will get these values, we put it into the function and then evaluate this combination. So this is the how we evaluate it. And then we use a policy to move from these points or to get these new values. How we do it? Just focus on the way how we music is developed. And the logic behind is also very interesting. Few songs which you heard somewhere 20 years back, even just listening one single note, you can identify the song. What is this song? And few songs which you just even listen yesterday only. I mean, you're still not able to recall it. That means there is something which you remember, and that is the melody. So the melody we remember, and that is the part you use here. Melody here is the function value. So if so good melody means but optimized value. So now the question is how you compose a music. So there are various ways. One composition is uh and this is an interesting domain. After this lecture, try at ending, try to find out, do Google search, you'll find all these things happening. Even a single note, you can easily recall who is the musician, whether it's A.R. Rahman or R.D. Burman or Anu Malik or something like that. How we recognize it? There are patterns. So the patterns appears because the way they create the music. So one way of creating a music is listen the music in some other language, say Korean language, and then around that build a song in Hindi. That is one way of doing. Second is somehow you have a good composition which was hit, and then just do some small changes near around that, you'll get another good music there. That is the second way of doing it. And third is you keep on trying, do random combinations, and finally you find out them. So those things are here. So we use all these things here. We use pitch adjustment, we use memory here, and based upon pitch adjustments and the memory and the probability theory, we develop this whole algorithm. So this one is a harmonic search algorithm. And then there are the parameters which we need to optimize. Means which not to optimize, which we need to work on if you want to develop a new variant of harmonic search algorithm. So we developed two variants of this one. You can follow this paper by us intelligent tuned harmonic search algorithm, where we modify the tuning parameters of harmonic search algorithm. This one is another algorithm which me and my team proposed. So initially I worked on this one. So this one is basically, I tried here to put two combinations there. So the challenge I put it like, if I start the algorithms randomly, purely randomly, and then in my search also there is a randomness, because of, you have seen rand is there in crossover, rand is there in your PSO, rand is there in harmony search also. So if there are a lot of randomness, and because of that, what will happen if you run these algorithms? Yeah, I'll take only 2 minutes to finish this one, then take your questions, and then we go for the next one. So if your algorithms are full of randomness, and that is a problem with harmony, these meta-heuristic algorithms. If you run these algorithms 20 times, you will get 20 different answers. And the challenge is then which one is the best. So how people report in the literature is, they run it for 20 trials or 50 trials, and then they report what is the best solution, what is the worst solution, what is the mean value, and how much is the deviation in the solutions. But the problem with these algorithms, if I want to put in the real-time environment, we face a problem. So we and that time I was working on honeybees. I studied honeybee and the behavior and all these things. I found that bees are the most organized species, uh, and their working is very well organized and structured. So taken few concepts from there and looking for an algorithm which is derivative free, and can we combine it so that we can make it more deterministic. Now there are two things. Deterministic means, try to understand what is deterministic. Deterministic means I know from where I'm starting, and I know my policy completely, so that I know where I'll be after that iteration. That is the deterministic. So I know every points, my movement points. Stochastic means I don't know from where I'm starting, and even I don't know where I'll reach, because there is the randomness. So it is basically try to make it deterministic kind of arrangements. So only we have taken only one aspect of it, and that aspect is basically the search method, which we have taken this one. This one is started with an article that the, the memory of 4 places, and this is inspired from Nendler's methods, which was proposed in 1947 or 49, 1947 around. So the search is basically these here. It searches 3 points, so one and these two, and based upon these 3 points, which one is the best? So say these two are the best. So then it calculate this distance and take a projection, search it here. If it is not good, then it will contract it, take a midpoint of these two, and likewise. So it is basically contraction and expansion. It's a geometrical search method, which is not a very new, but this we try to connect it with the hypothesis that the 4-point memory of the bees. Rest is how they send the things, how they observe the things. So you can see this behavior is interesting. So we have just targeted this behavior. There are a lot of other behaviors of honeybee. So you can see here the bees are starting it here, and they keep on search. These are the scout bees which go for search. And once they get a food, then with respect to sun and their place, what is the angle? They remember it. And when they return, then they make a dance, which we call it a waggle dance, which is in the form of 8 like this. And the axis of this 8 will give them the in, information that where is the food. So if the bees are dancing like this, then with respect to sun, how much is the angle? That will be the angle here. And then we use two kind of a decision making in bees. One kind is quorum, and this is consensus, because many bees go for the search. So how they take a decision that which food is good. Food means in optimization. Food means my solution. So there are two ways of doing it: quorum and consensus, and which we have also applied here. Why we call it a directed bee? Because we structurized it. It's not like randomly they are going. So whole of the space we have structurized equally into some small blocks, and then we performed many experiments, and we found that the best point to start is at the center of that box. So we direct a bee that, okay, you search it at the center of the box there. That's why we put the name directed bee colony, and then performed various experiments, and we found that there is a uniqueness in the solution, so that we get rid of that issue that every time we get a solution. In many of the benchmark, most benchmark problems, it performs better, and it is more suitable for real-time application. Okay, so there are many more, but I'm not going for those things because of the short of time. The idea is just to tell you, okay, that how it works. Just I'll give you an idea. You can go and search it. So this is one which we have proposed. The another we have proposed on the modification of the gray wolf, which is inspired from how gray wolf work, which is known as beta gray wolf. You can check it from this article. The another one is whale optimization. So the whale, they form a spiral movements, and that property is used to move from one point to another. The another one is the edge spider monkey. So this one is basically we have added the concept of aging effect. This article we proposed in this method we proposed in 2016. And then okay, seven sister algorithm. We propose this algorithm inspired from the seven sisters. They are working in 2023, just 2 years back. And then IWD was proposed by Hosseini, that is by how the river formation take place, and then we modified it to intelligent water droplet algorithm. Firefly is algorithm which is inspired from the fireflies, how they attract towards the light. That's the idea here. And then simulated annealing is a very old method proposed in 1987, inspired from how the cooling effect appears in, you can say, in how we prepare the things up uh, with cooling process. So it's a thermodynamics and mechanical engineering part. Fish scowling, how the fish they form different shapes to save themselves from big fishes and all that. So that is fish calling. That is a policy here. BAT algorithm is basically how the BAT transmit the waves, receive it back to find out the object and save from the enemies. So that is the policy here. Cuckoo search is basically on how the cuckoo lay the eggs in some other species, and then how those eggs will survive, how the things happen there. We know that cuckoo put lay the eggs in somewhere else, and that is grow one, and then how those things happen. So that policy and the working behavior, uh, this algorithm was inspired from that one. Biogeography, basically how the species move from one island to another one, and they stay and then they return back. So that is basically biogeography method. Bacterial of foraging is inspired from bacteria. This is E. coli bacteria present in every human, and then how the bacteria move with the, if the food is good and the food is bad. So this behavior is adopted to find out the solution, which is known as bacteria foraging. Yeah, sorry to be very fast on this one because there are a lot of algorithms. So uh, I just explained only two, three of them in detailed one, but you'll find a lot of algorithms are there. So any questions from your side? I can see, I can expect many questions here because I'm not able to explain everything in this constrained 1 hour lecture. So if you have questions, please let me know so that we can discuss your question, your queries and all that part. Yes, please, questions from your side. Yeah, so the question is, okay, let me start with. Yeah, so which is the best method? And my answer to this one is there is a theorem which is known as a free lunch theorem. So no free lunch theorem means there is no universal algorithm which is good for all. So you can't say that this algorithm is the best. Okay. Uh, so the algorithms, like, you, you have to check it out, the problem. Like if I'm looking a problem which is more of a kind of a path kind of a problem, so then we know that okay, ant colony is more like a path movement which is inspired from that. So probably that will be good to use it. So another algorithm which is path like it's a river formation, that is also path kind of a structure. So depending upon your problem, you have to figure it out which method is good and which method is not good. Okay, we can, okay, fingerprint recognition, we can use it. See, uh, solving an image or recognition problem. So what, how you formulate it, that is important. So the, if I formulate it that, okay, I take these features, and I develop a loss function which consists of the difference in the feature, and then my objective is to minimize the loss function. So now I convert this problem to optimization problem, and now I can use these algorithms to solve my optimization problem. So it's totally upon you that how you are designing the problem. You can use it. So you can convert your problem to optimization problem because of the limitation of time and all that. No, I'm put some I mean, it's like examples are not there, but I think in the next lecture we'll discuss that how you can convert a problem to one form to another. So if you are working on the image recognition, convert that problem to optimization problem, and then you can use these algorithms to solve your things. Okay, so the next question is selection of parameter values like iterations and PSO, any range, any criteria. Okay, so so there are some discussions, and the discussions are already there. Like if I, the one thing is PSO means like how many agents I want to use for my search. So just think of that. There is a room of say 10 feet by 10 feet. If I use only one agent to search it, it will take a lot of time. And then if I use 100 agents, probably either you cannot fit them or they cannot move. So number of agents you have to choose it. Okay. So that again, I'll say that again varies from problem to problem. If my problem is very complex, I have to go for more agents. If my problem is simple, I can take a simple one. Thumb rule is something like people work with around 30 agents, 30 search agents, and all that. For C1 and C2, again, whether you want to work with a static or dynamic values, static, the thumb rule was taken initially. There was no any such proof that time. People choose C1 plus C2 is equal to 4. That is a thumb rule. But later on, people discovered it that if you make it variable, then we can have a better way of getting the solutions. And then uh, later on, people are working on the stability side of it. Mathematicians they jumped into it and then try to find out what are the most appropriate and stable values for certain kind of problem. So the parameter values they change. You have to choose as per the problem complexity, and that's why if you are working on optimization, my suggestion is I usually ask the student and means like when they are proposing anything new on it, what is the complexity? How much is the complexity of your problem? If you are looking in this domain, my suggestion is just check out the complexity of your problem, and after that, go for your methodologies and all these things. Okay, any more questions? Any more question if you have? Okay, so your question is how to control the number of features, how to limit it. Well, you can put it the upper limits, and then if you want to make it them dynamic, like omega is there. I'll just give you an example. So omega is controlling the initial velocity. So initially I want a high velocity. Okay, so I keep a high value of omega. But after some iterations, high value of omega means if my value of omega is high, then every time when I calculate the velocity, that value will be high. If that value is high, then I'm adding a high value to my initial point to get a new point. That means my search points are far away. And that is basically I'm jumping from one point to another point, which is far away. And that is basically I'm exploring my surface. But with time, what I want to intensify. So I want to exploit the thing. And that is basically how you search near around the best solution. So, and at that situation, my step size, I want less. So omega has to be less. Okay. After certain iteration. So it's a total balancing between exploration and exploitation. So now if I'm putting, this is my objective, then what I want is initially in the start, I want high omega. And then with time, I want the reduction in omega. So now instead of taking omega as a fixed value now, what I'll do is I make it a function, decaying function. So you can decay it linearly. You'll find certain articles, new algorithms. You can decay it exponentially. You can decay it stepwise. And that is a new variant there. This is how you can put a limit, and this is how you can make the things better for your algorithm. Hope I'm able to answer your question. Any more question, please? Okay, no more questions. Okay, so no more questions, ma'am. So can we
Yes.
start after 5 minutes or
Yes, sir. Yes, sir. After 10
okay?
minutes also is fine. We can start after 10 minutes.
Okay, we can start after 10 minutes. Okay, fine.
Yes.
Though the time is there, it's already 3:15.
That's okay, sir. That's okay. No
Yeah.
problem.
So I'll start, ma'am, after 5 minutes. No worries. I'll take a break of
Okay.
5 minutes and then I'll start. Thank you.
Okay, sir. Okay. Thank you, sir.
Hello, ma'am. Can we start now?
Yes, sir. Yes, sir. We can start.
Okay. Okay. Welcome you all in this session, and this is on neural architecture search algorithm. This is a part and all or one category, and we call it the auto ML, which is relatively a very new category of AI or machine learning. So we call it auto AI or auto ML. And our discussion is more on neural architecture search, how we can do it. So this is from where we have started this course, that okay, we are given certain kind of features, certain kind of values, and this is the outcome. And then you asked to develop a model so that if I give the two inputs, then it will give me that this is my output. This is a true false kind of a tabling there. This is the beginning of the course there. So what we did is like we convert it into some kind of numbers, and then check it out that what is the output, how it is there, and then finally what you based upon the input that okay, there are two inputs, there is one output, you develop this gate, this neural network, and finally you find out these values there. Then you choose, okay, let me take better. Then you choose a threshold there, put some activation function which give you that if you give 0 0, then output is 0, or if it is 0 1, then output is 1, and likewise. And that is, we call it it's a neural network representation of a digital circuit, which is OR gate. This is a simple way we have started. And then later on we found that okay, this is a simple one, but if my data points are complex. So this one is a single simple linearly one line can help us in separating it like this, that if any of the quantity is 1, the output is 1, else it is 0. So it's a simple one. We can draw one line, and that is basically called a decision boundary in neural networks, and that will help us in identify the things. But if the things are more complex, like then we need to go for a higher one, and that's basically inputs are same, but now if there are two decision boundaries, then what we have done is uh, we have introduced another layer in between. We call it a hidden layer, and then there is an output layer. So this hidden layer so this one circuitry, okay, x1 x2 with n2, this one path give me a one decision boundary, and then x1 x2 with this path give me the second decision boundary, and then data are separated that inside those decision boundary they did those data belong to one category, and outside the decision boundary they are different category, and this is XOR gate, and this is how we have developed it. But the point is, since now the complexity is more, you have this we have introduced layer here to meet that requirement. The complexity is less, then we go for this easier one. Well, now let's go for the another level of it. Let's increase the complexity. Now instead of data points, I give a value, I send a face. And then what I'll do is from the face, I take the few features, that there is a nose, left eye, right eye, lips, ear, left ear, right ear. So these are features. So I have 1, 2, 3, 4, 5, 6 features. So I know input layers are 6. Then I introduce hidden layers in between. These I have taken some number, and then output layers. You can take as 1 also, you can take 2 also, and then try to find out what is this? This is a phase or it's not a phase. You can take it, if you are taking 2, then the common answer will be in the form of 1 here and 0 here. If it is a phase, if it is not a phase, then it is 0 and 1. Likewise, and if you're taking only one output, then either it's a 1 means phase, it is 0, no phase. But the point here is, since here is now complexity is there, you cannot uh, bifurcate only with the single decision boundary. You need many lines there. So we have introduced layer into it, and then we have put a lot of connections there. But and then what we do here is we use certain kind of algorithm to find out what are the weights of these connections here in between connections. Well, this works fine, but this method works fine, but this method totally depends upon how good I am in extracting these features. If these features are not well uh, generated or produced by me, then this model will not perform good. Okay, so that is a challenge here. So this is basically how it worked. It like I give some numbers, and then I look for some numbers, and then check it out what it has to be. And based upon that, I propagate back and find out these numbers, which we call as the weights. This we do it by method, and one of the most common popular method is uh, your back propagation. So what actually we do in back propagation? We know we just initially we start randomly, and then we give some input, find out the output. We know that what is the output value, and then we also know that what is the actual value. So based upon that, we decide about how much is the error. So we develop a error function. We call it a loss function. So if this is the structure, now what you can do, where you can do the change. So you cannot do the change in the input side because that is the data. You cannot do the change in the known values of y because that is also data. Structure is fixed. So the change is you can change these multipliers, which we call it the weight. So we modify these weight in such a way that the error is reduced. Now it's optimization problem that minimize the error loss function by changing the weights. And one of the way which we have seen it's a back propagation. So back propagation it's a gradient way of doing the things to find out the solution. And then people talk about something else. They increase because the accuracy is not good. What they have done is they have increases the layers. Okay, so what they have observed is like if I pass this image and take this structure, so this structure gives me certain output like this. It's not like, and then if I take this one, and so they have what they have done is this is the whole arc structure from here to here, and then they try to observe in between what is happening. So if you see at this layer, you'll find the images patterns will be like this. If you see the images at this layer, you'll find some kind of extractions. If you see at this layer, you'll find certain faces. Finally, it's recognized there. So that means something is happening at every layer. Well, that is basically what is how they think in that way. So then there are different questions because if my weights, if I have trained here appropriately, then this will be good. But if these are not prepared, developed properly, this will be bad. Or if these weights are good here, then this part may be good, but not the other part, and like this. Because the error is propagating like this if you use back propagation error. But at the summary, the goal is to minimize the loss function total error. So one way of using meta heuristic is this one, that instead of propagating the error back and all that, can we use genetic algorithm to find out all these weights so that the loss function is reduced? Okay, so we define the loss function, and then we apply this is a genetic algorithm, and then we find out the weights. The algorithm keep on running in a loop so that the error is reduced. So the error is now how you are defining error or which error you want to reduce, that will be objective function. So if you want to reduce the mean square error, your objective function is this. If you want to reduce root mean square error, this is the objective function, and likewise. So this is the way you can use meta heuristic in one go to find out the solution. Well, this is not Nash. This one is finding the weights of that one. Well, if I change the thing a bit more, that I know not only the weights here, that is important, but also the important is what will be the activation function. Okay, what will be the learning rate? What will be the, if we are, how we can avoid your overfitting? So I have now many questions with me. All these things, like what will be the optimal learning rate? What is the best learning rate? What is the regularization parameter? What type of activation function can I use? These are known as hyperparameters. So now I modify my problem, that this problem I'll solve by using genetic algorithm. So what genetic algorithm will do? It will minimize my loss function. At the same time, it is giving me optimal values of weights, also giving me the optimal activation function, because I know there are a lot of activation functions. So which activation function is good for my problem? And this is the question every time. Last time also people asked that which activation function, what should be the learning rate, and all these parameters. So the answer to this one is I'll make all these as a variable. So the output is now just like, we can make it like this. You can take it my loss function, which is now it's a function of my real value. So I know what is my real value y, and it's a function of my estimated value, which is y hat, which is now again a function of this y is now as a function of all the things. Okay, so you can put all the things here, things like learning rate, things like activation function, okay, things like weights, and if you are interested in something more, you can put all those things here. This is hyperparameters. Okay, so if I do it like this, so I get rid of few of the things that, okay, what is the good value of alpha, what is the good value, which activation function I have to use, what is the value of the weight, and some other parameters. So this is known as hyperparameter tuning using genetic algorithm. So we have just automatize it in a way that now my this algorithm, genetic algorithm, solve it and give me the most optimal neural network. Okay, then for people further add more things to it, that okay, can I add the test and training split also in my as a my variable there? You can do that. So you can, so whatever you feel that okay, this is a challenge to my problem, you put those as variables here. Well, if you put many variables, you'll find the problem complexity increases. And if it increases, then your classical way of doing back propagation of that will not set meet our requirements. We have to go for other methods, and you can use meta-heuristic methods to find out the solution and all that. This is hyperparameter tuning using some algorithms. But we know that in deep learning, uh, better is why we are going for deep learning. The answer is simple, that we need not to do the feature engineering. Before deep learning, whatever we do is we do a lot of feature engineering. But in deep learning, it's more on the other aspect of it. We are making a algorithm also to learn the feature. So it's more on not feature, it's more of feature learning. So at every layer, you can see here this layer, it learn these features. At this layer, it learns this feature. Is this layer, it learns this one. Finally, it recognize it. So this is what we have discussed in last time when I was talking about the CNN model. So we give an input and then we have convolution, then we have pooling, then convolution, then pooling, something like that. So some part of it will learn the features. That is basically known as feature learning. And then we talk about fully connected network on all these things. That is basically the classification part. So that is the challenge. That is the two operations we put together. And that's why this network is quite big one. This whole structure is quite big one. And that is one kind of a challenge. Then we'll see in the coming slides what are the challenges and then how people try to address it. But this is what is called as a deep learning. And this is Alex model. So we discussed last time, deep learning, when we discussed it, we pass an image, we put one convolution layer of 11 cross 11 filter, then another convolution, and then we have convolution 3, 4, and then 5, and keep on doing. And then finally we have fully connected network, and then we can use dropout there, and finally we will find out. So after the fully connected, we its a job is classification. But before that, what it is doing is it is learning the features or extracting the features automatically. So if you summarize these things, last time also that is what we discussed. If you summarize it, it is actually what is happening, that they are playing with these things. Like we have three is the operations, okay, and input is basically one is convolution. Maybe you can use another layer of normalizing if you want to work on that one, pooling, dropout, and then you can use in various forms like series connection, and later on you can flatten it, and then you can put dropouts, and finally you have answer with you. The arrangements are different. So this one is one arrangement, the simple arrangement, okay, repetition of these blocks. So now let's take it. It's a convolution block, there is a pooling block, and then you're repeating it again and again and to get the solutions done. That is one of the arrangement, but this is the another arrangement. Okay. I'm just repeating the things because I'll take that question which was asked yesterday, and then we will talk about these methods there. So that we have combinations like this, and then we divide it parallelly. Then we have parallel combinations. Then we combine them. So we have various kind of mode. We can go sequence, we can go parallel, then we can go combining them and try to find out the solution. And then the complexity is more. Then you can put a, and this one is another kind of arrangement, that is basically when you talk about the inception. So inception layer was introduced. So we have inputs, and then we have movements like this, and then it keep on moving. And you can see now the structure is quite big. You can see the blue color is convolution blocks, red is your pooling blocks, and then soft max. So we have different outputs, and then we'll see which output is good. We take it from there. Okay, and then this is towering complexity. You can see the towers are built up, and each module has a different level of complexity. And the challenge is like how to how to justify the structures there. Like Google Net. This one is Google Net architecture, so that each block is stacked basically. So in each block there is a inception stacks and all that. These are the common architectures. I have just taken it. that how people are working on these modules, and why we are talking about a new AutoML. This is ResNet. We have already discussed, but ResNet we can see that there is a residual block. So the block is connected from here to here. Okay, these are the residual blocks. So there is a bypass mechanism. But maybe somebody may ask it, why from here to here? Why not here to here or here to here? So how long how long would the bypass should be there, and likewise. So there can be n number of questions. And we will try to answer those questions. We will try to all these answers, and that is how the people they are doing research. And the question is, this is very interesting slide I found, that why so many neural networks? So you can see that accuracy versus the operations, and that's why that is basically the reasons. So how many operations you want on this side, okay, and then you can see the accuracy level. So accuracy level you can see somewhere is an inception block. Okay, the operations, basically the bigger is the size of the block, more operations are required and all this. So you can see a lot of modules are there. So if you go for less number of operations, what is our goal? Our goal is always to operations should be less and accuracy is as high as possible. And that's why people keep on developing new models. But what actually they are doing in all these models, they are just arranging the blocks in different manners and all that. Well, this is fine, and this is what we are looking for. And what is the challenge? Now, the challenge is, most of the time, these structures, these are designed by the experts. Okay, so this one person is expert of AI, so they design the neural network. Okay, this should be the size, and increase this. This should be the, take this one as a filter size and all that. But many of us, they are not expert, but they want to use it. So then the challenge is, how we can make it uh, suitable for those who are not expert of this design. Well, this design is better or this design is better. These are just take it in blocks. So if I connect the blocks like this, or I connect the blocks like this, which is good? So one way of doing is, you develop this module and then you develop this module, check both the modules and see which one is performing good for you. But I don't think this is an optimal way of doing it. And that is exactly what was the question yesterday raised by someone, that how we decide how long is the module, or should we go for parallelly, and all these things. And then there are certain other points are there, and the logic is, people put it like, okay, now we are working on AI, which is ultimately we are looking for to make it fully automated. So can we give this as a challenge to our algorithm also, that okay, you design of your own and give me the best model. And that is how the starting point occurs. So like the challenge here, so if the person is a designer, he knows that okay, you connect it after every two, and then consider this one as this length, and you'll get okay, what is my accuracy. But the but the question is, okay, why after two, why not after three? Or why it should be like 4 and 4 and 4 and 4? Why it not be 4 3 4 2? These questions, designer can give us kind of suggestions, but because they have done a lot of experience, but for beginners and the most of the people, they are difficult to answer it. So instead of putting it that, they say that like, okay, can we, this is a child's game now, so can we so what any of the scholars they are doing it, they are trying various combinations, and then they come out that okay, this is the best model, and give a new name, and they say that okay, my results are better. But AutoML talks about can my develop my algorithm in such a way that it automatically design the structure and then give me that okay, this is the best structure to solve your problem. So the problem statement is like this. I have now so many things with me. Okay, so many things. How many posts should I use? What should be the batch size? What should be the learning, regularization or not? This is what we have discussed, hyperparameter tuning. On the other side, how many layers? What are the type of layers? CNN, LSTM, pooling, fully connected, and all that. How many layers? How many neuron in each layer? How many filters? What should be the filter size? What is the kernel size? So you can see the questions are too big. And then what we are looking for, we're looking for an approach or methodology that answer these questions. And that is basically, we talk about AutoML, that is, and there is a part in it that is known as neural architecture search. So what is the job of neural architecture search is, given this one input, it will give me the whole structure, the best structure. That is what people are looking for. But before that, before going to that one, they worked on different more aspects of it. Okay. So one aspect is this one. This is many of the students and research scholars, they are using it. They say that, and that comes a bit before that, instead of developing the whole, we know that, okay, this model, say VGG16, already we know that this performs better on X-rays, say. And now my problem is a typical kind of X-ray. So what I can, so we know that people have developed it and it's available. They have tested it on, say, chest X-ray. And now I want to implement it on my knee X-ray. Maybe complexities, yeah, we know that there's a difference. So what they suggested, like you take the same model and then just play with certain parameters, outer layer parameters, and then use it for your purpose. This we call it a knowledge transfer. And this approach is known as a transfer learning. So we need not to worry about that how long it has to be, because it is already there. We just play with the parameters at the outer layer. This is one way of doing it. But the other way which we are looking is totally new. So I have so many parameters, so many models. Out of that, which is best? And that is basically the job of neural architecture search. So it, out of all these parameters, it make various combinations. And out of that, then finally it will give you that this is the best combination, which is giving you 97% accuracy. Okay, so so now there are three parts there. Okay, in Nash, one is the search space. Now, search space is very important. So I told you that this is optimization, and then when you talk about the optimization, it totally depends upon the search space. So if I keep everything open, like how many layers, what type of layers, how many layers, neurons, dropouts, filters, kernels, learning rate, everything here, my search space will be very big and it will take a lot of time. But if I fix something that, okay, filters, I'll choose always 2. So then my search space is reduced. How many filters? That I've kept open. Dropout, I fix it that, okay, I'll take a dropout of 20%. That means 0.2. Now my search space is further reduced. So you have to choose it carefully, that what is your search space, because then Nash will give you the best option from that search space. So instead of making everything, if you make everything open, no worries, it will do, but it will take a lot of time because the space is multi-dimension and you have to find out what is the best solution. But if you restrict it, you just think of that like, okay, I have X, Y, Z, 3 variables. So I have to search in 3D plane. But if I restrict Y, that, okay, Y is this much, then I have to search in X and Z. That means I have to search in 2D plane only. So my complexity reduces. That comes here. And then the way of searching it, because the name is neural architecture search. How you can search it? So they are common, a few popular algorithm. One is grid search, random search, Bayesian search, genetic, dart, RL. I'll discuss few of them. And then you have to fix it. What are your performance matrices? What it has to meet at the end of the day. So that will be the flow of the situation. So these are the most popular algorithms. One is reinforcement learning method. Another one is neuro evolution. Another is differentiable architecture search, that is known as DART. Another one is one shot Nash, and another one is the training free method. So what is the reinforcement learning? It was proposed, the article is already there at Archive 2016. So here is basically, this one is totally based upon the reinforcement, where there is an agent and it takes an action. Action goes to the environment and environment give a reward. And based on the reward, it modify. Here we call it a controller. Okay. So here in this paper, they have used RNN, recurrent neural network, as a controller. So what it RNN here, it will give, it give one combination of the structure. That, okay, I'll show you the figure also, that this much of pooling layer, this number of your convolution layer, this is the function, and this is the sequence. So it gives one structure complete. Then once this structure is taken, then the data which are available to us, we train over it. Here, the environment will train over it. It will give the accuracy. So say if the accuracy is 87, then it will give this accuracy 87. Then you can put it, I'm happy with 87 or not happy with 87. So you are happy after say after 95. So 87 is less than 1. Then it will give a reward of negative reward, that modify your, give me the new combination, or modify your, or update your parameters. So it will update its own parameter, give a new combination. Then the new combination comes here. Again, we train it and check it. What will be the answer? And it keep on doing it till it achieve that or satisfy your requirement. This is basically reinforcement learning based Nash. So the structure is created by approach which is known as a reinforcement learning. Okay, so this is like, it will work like this. You can have it give a sample of architecture from the search space. Okay, and sorry, controller given structure, then the action is taken. That means that will pass here. It gives a solution, and it will keep on repeating that. Okay. So we are not talking, not going to talk about RL. We already know what is there in the RL. Okay, so there are various methods of RL, but here RL is used as a designer. So RL agent or controller give you structure. Structure goes to the real environment based upon the environment reward. So how it will work? You can see it here. The layer we have fixed it. Okay, we talk about fully connected neurons we put it, but we need a structure there. So it will generate a child network. It will train. We'll get the accuracy based on based on this accuracy. It will update its policy and then recreate it, and this loop keep on moving till you get a very high accuracy. This is automated uh, creation of your uh, neural network. So it is something like, it start with small packets, and then slowly it keep on building it and give you the final outcome. So here you need not to worry that how many layers and then how many filters and then how much is the learning rate. Nothing you need to worry on that. It automatically do the purpose there, but it's a slow process. So this is how the RNN works. If you are aware of RNN is always like this. So you can see the output of each block is here, the number of filters, filter height, filter width, stride height, stride width, number of filter, and they have choices. So out of these choices, finally you'll get this combination. This combination will go to the structure. So the structure will be formulated. Once the structure is formulated, data goes to the structure, and then it is trained. We will get the accuracy that, okay, this is the accuracy of that structure. That comes back, and then that will update the parameters. Once it update the parameters, then these value will change. Based upon these value, a new structure is created, and that will go, and then data again pass through it, train, and then validate it, and you can see that accuracy validation. You're happy, it's okay. Not happy, again the process keep on working there. That is RL based. This is another way, that is known as neuro evolution. This is basically everything is designed, the things are designed in a evolution process. It's like a genetic process. So we have totally different combinations, and then we just check it out. What is this combination is good, or this combination is good. So we have, it's a kind of a innovative. So it's an evaluation process that is being used here to get the job done. The third one is differentiable architecture. So most of the problem, like what we have seen here, it's a combination of these blocks. Okay. So the combination of these blocks are, we know that they are discrete in nature. They are no more continuous. And if they are discrete in nature, we cannot go for differentiation and all that. So what Young and his Liu and the team, they have converted the discrete form to a continuous form. That So instead of the connections like that, they have formulated this problem as a continuous problem. And if it is a continuous function, then we can use a differential. We can apply the differentiability. And then they put a pathways in a continuous form, and then try to find out which path is better. And from there, they propose that, okay, this structure, that is input here and output here, this structure is the most optimal structure or best structure with these certain value of weights and all that. This is known as DART, and that is differentiable architecture search. This one is one shot Nash. This is very recent, proposed in 2022, and they talk about that. Uh, let's talk about there is a supernet, and then we just work on the subnets only. So we work only on the internal part, outer part we keep it fixed, and the learning is very fast. It's a kind of like one shot kind of learning, and that's why this one is known as one shot Nash. And then comes here, it's a training free methods. So in earlier we have training, but this is heuristic one. So we have combinations. Now we are not going that way training the things. What we do is we have one so like we have 30 agents in PSO. So 30 agents means there are 30 structures. Each will go with certain kind of weights and all those things. They take the input, find out the value, which that is basically which one is giving the highest accuracy, and then based upon that highest accuracy, we modify the structures. So they call it a training free. Also, they talk it's a evolutionary. It's a one step ahead in the evolutionary, and that is basically we don't need a internal training. So if you want to use it internal training, you can use it. But here we can skip that part also. Well, this out of these four methods, five methods, if I talk about here, out of these five methods, first three, in fact, first two, they need a lot of computing, take a lot of time and high computing. Whereas the last two, they are relatively very light in execution, so they don't need that much of computing there. Okay, and Dart is somewhere in the kind of between structure in there. Okay, so going further, like this is one of the application you can take it. So what you can do is you can use a genetic algorithm to give you the best architecture. Okay, so what you can put as a variable, you can do this genetic algorithm. You can say that data, these are fixed data, but I fix and the input nodes, I know there are 3 input nodes that I also fix. I fix the output node, that is one, fine. And then I'll say that number of hidden nodes, that is variable. Okay, that is first thing. Then neurons in each hidden node, that is also variable. Then type of the activation function, that is also variable. Weights, those are also variable. And the structure is also variable. And now you use genetic algorithm to give you the most optimal structure. That is a simple way of representing this whole complex idea there. Okay, so this it goes like this, like first individual it will take like this, it will take another individual like this take another individual like this, individual 4 is like this, and then it perform crossover. This, so this structure which is there on your screen, that can be coded in form of 10101010. Genetic algorithm operates over these 10 values. It will give you a new population. Then it will, once it has a new population, then it perform crossover, then it perform mutation, and then it will give you a new population. New population means new structure. And then you take that structure, train it, get the accuracy. That will be the evaluation. And then go check the survival for the fittest, and the loop keep on working. These structures keep on changing with every iterations, and finally you will get the most optimal structure for your problem. That is how you can use these meta-heuristic algorithms as an optimizer to design your neural network. This one is what I'm showing. It's for a simple network, but yeah, for a complex network, these are you can replace all these terms with the blocks. Each block is kind of like has a variability that is basically uh, what is the filter size, what is the filter length, filter breadth, how much is the stride. So convolution filters, you have your convolution blocks there. Then you can have max, you have pooling block. So which type of operation you want to use, max, median, mean, minimum, likewise. And then you have a ReLU function. If you fix it, it's okay. But if you want to try on 3 or 4 methods like leaky ReLU or ReLU or stiff ReLU and all those things, then there is another variable block. And then how many of these blocks, that is also a variable. And then what will be the sequence of these blocks, that is also variable. And then what is a skip connection, that is also variable. And then how many parallel and how many in series, that is also variable. So all these things you put it, and then use all most popular 5 methods I have shown you. You can use any of them, or if you want to use heuristic one, you can use any heuristic algorithm, which finally will give you the most optimal structure there. So that is a part of a neural architecture search. So now we have things here like search space. So what is our representation? What is cell block and meta architectures? Then you can think of optimization method, whether you are going to use reinforcement or evolutionary, or even you can try gradient based also, because the Dart, they are using gradient based approaches because they have converted the problem into the continuous functions. Or Bayesian optimization, you want to use it. And then evolution method, what you want to use? You want full training, you want partial training, or you want hyper networks or something like that. And then once these things are there, these models are ready, then there are popular benchmarks. Suppose you come out with a totally new model or new methodology. Say you want to combine your whole this Nash with, say you want to use PSO with that one. So then there are benchmarks which are known as Nash benchmark 101, 201, 301, and NATS. And then check on it. If it is performing better, then you can claim that, okay, this kind of approach or this kind of methodology. So in optimization, when you propose it, you'll find there are benchmark problems. So if you just check over it and then compare it and put it, that okay, my method or my algorithms are better and how they are better. So already people have already published the things on the benchmarks, and then you can compare, and then you can prove your hypothesis there. Well, that's in a compressed way. Yeah, I have put the uh, try to explain the Nash. So Nash is basically, now again let's summarize the thing before I'll take your questions. It is a way where a designer need not is not required. Designer expertise is not required. The algorithm itself decide everything. So it decide that structure and the most optimal or best design of a neural network for your problem. That is basically uh, that's basically all about with Nash. Okay, so now I'll take a questions, and then we can